Industrial processes like the manufacturing of steel, cement, fertilizer, and petrochemicals, especially plastic, account for 1/3 of our global energy use. The world now produces annually about 4.5 billion tons of cement, 1.8 billion tons of steel, and nearly 400 million tons of plastic, and 180 million tons of ammonia. Their manufacture requires high temperatures, which is often the case. The heat comes from burning fossil fuels. What is the path to decarbonize industrial processes? And in this episode, we talk to two researchers from the Payne Institute for Public Policy at the Colorado School of Mines about their recent work of green steel. Let's welcome Anna Littlefield and Edikan Udofia. All right, well, hi, Anna and Edikan. Thank you so much for joining us on this episode of USC E-CET Energy Transition Talk podcast. Can you tell us a little bit about yourselves? What attracted you both to the topics of green industrial processes and carbon sequestration?
Well, I'll go first. Thank you so much for having me. My name's Anna Littlefield, and I work at the Payne Institute for Public Policy as the CCS program manager. My title's recently changed a bit to low carbon energy lead because I've also been working in topics like geothermal and hydrogen, so not just carbon management. What first got me interested in this space? Well, I'm a geologist by background. I'm a current PhD candidate in the geology department here at Colorado School of Mines. So I've always been interested in energy and earth science processes, and I worked in oil and gas for many years. And I think I've been interested in industrial decarbonization, specifically just because the skill set that is needed to address some of those issues in the hard to abate industries or difficult to decarbonize industries has a lot of overlap with the work that I did in oil and gas. So a lot of the same subsurface expertise for my PhD specifically, a lot of the geochemical considerations that we have to take when we're modeling what happens when you inject CO2 into the subsurface. There's a lot of overlap there, and it's always interested me. And I think just kind of finding a solution to some of the problems that our society's heavy energy appetite has caused is appealing to me. I'll turn it to you, Edikan.
Oh, thank you. Thank you so much, Anna. Hi, Mila. Hi, Roshan. So my name is Edikan Udofia. I'm currently a PhD candidate in operations research with engineering, also at the Colorado School of Mines. Um, so I have been in the extractive industry, like I have a, like I have been, I have about 12, between 10 and 11 years of work experience in that field. And I came to Colorado School of Mines, and one of the things that made this whole area of like overarching area of sustainability attractive to me generally is the fact that I mean, in the direction that the world is heading, where there's going to be a lot more automation, um, whatever we can do in some sense to ensure that the the our traditional industries still stay relevant in a way that has like far-reaching effects and far-reaching um, influence. I am a big supporter of that. So that just made me dig deep at the time when I came first for a master's in mineral energy economics, and I just I got introduced to the topic of energy transition, and for me, my biggest interest in it is safeguarding the future, but at the same time ensuring that that we can still make the industries that are relevant stay relevant slightly longer. So that then just introduced me further and further into the world of sustainability and decarbonization of heavy industries. And my current research in my PhD program has a lot to do with process flow optimization, scheduling optimization, industrial scale data analysis, and it just made sense that we could see where the two meet, and this world of decarbonization of heavy industries just happened to be a perfect fit for both.
Wow, thank you.
Yeah, yeah,
And now I think you've both recently written a paper on green steel. Could you
that's
guys elaborate
correct.
a little bit about what green steel is and how that differs from traditional steel manufacturing?
Okay, I'll go. So, traditional steel uses coal or coke, what's called metallurgical coke, which comes from coal, from a certain kind of coal, uses it as a fuel and also as a reducing agent. And this has been the practice in steel manufacturing for as long as steel has been a thing. But then the thing about this thing is that it's very heavy and highly carbon intensive process, right? And just this traditional steel manufacturing by itself accounts for about 7 to 9% of global CO2 emissions. So in the world now as we know it, exploring and how to still stay relevant, but then have a smaller carbon footprint is how green steel became a thing. So green steel uses hydrogen as a reducing agent instead of using coal or coke. And then typically also the electric arc furnaces that are used to melt down the ore, or the furnaces that are used to melt down the ore in like real pure green steel production value chain uses renewable energy for that. And then if they need other sorts of like fuel or reducing agents, they use a lot of bio fuel. So what now? So that is the green steel that now it and like kind of like encapsulates it from the very beginning of production value stream. But another approach to it now is where like people like Anna come into play, which is where there's the potential for carbon capture integration, which would then mean that at every um, point where steel is being manufactured, whatever carbon would have otherwise been emitted is now being captured. So that still falls into the area of green steel, but but pure green steel, like green steel in its purest form, every component of it like does not emit any carbon at all.
And I'll just
And would
add
it
a
be
little
possible
bit
then?
of big, oh, I'm sorry. I was just going
No,
to
you go
say, taking a step back and like adding a little bit of big picture kind of to that good technical commentary is that, steel is really, I think we talk about it in our paper as being ubiquitous in our society. And we would not be where we are today from an industrial perspective, from an economic perspective, and just development of our society without steel and some of these other heavy emitter industries. And one of the, kind of global perspectives is that we can't expect developing nations to halt all of their emissions as though they are at the same point that we are in our attempts to decarbonize. And, we would not have been able to do these things back in our industrial age, when it was really starting to kick off. So we have to think about the social component to this type of work. And Edikan did a great job of outlining some of the technologies that are using to address the steel manufacturing, because the energy shift is going to have to include an industrial shift in a lot of
Yes.
capacities, and trying to make sure that there aren't whole societies, whole nations, groups of people, communities left behind as part of the energy transition is something that we work a lot on at the Payne Institute, and are very, very passionate about and sensitive to. So finding solutions that allow these industries to continue to function in maybe not the same capacity, but a similar capacity is really critical.
And
Yeah,
when you're talking about how ubiquitous that steel is in our society, I can think of like cement as being also very useful or
that's
very
correct.
ubiquitous as
Yeah,
well, in the
yeah.
similar kind of category that you're talking about. And would it then be possible to make a green cement? Would that be viable?
So yeah, I know there are efforts on the way. Typically, also, one of the things that makes cement maybe so carbon intensive is when like the process of actually like reducing the limestone and what it is that I guess cement could where it could come to is also finding like alternative reducing agents and fuel sources. Cement manufacturing takes a lot of like the boilers will have to really work quite intensively, and I know there are efforts underway as well to see how that is. There is a pathway to us seeing cement also, receiving maybe the same level of innovation that we are beginning to see in steel. And but like Anna really pointed something out. Um, Steel and cement pretty much make up the built environment in a way. And I mean, we're looking at a world that is making all these advancements, and right now it is such a delicate balancing act, which is one of the things that Payne Institute is looking at. So we don't just come from an angle of just, okay, we'll just write policies because we want to look at it in that angle. It is the fact that you're looking at billions of dollars that have gone into capital costs to build, the facilities that there are right now. You're looking at tens of thousands, in some cases, hundreds of thousands of direct jobs that are being immediately affected in some sense. So I know that with like cement, the technology is evolving, and I know right now that they're looking at different, even like the sorts of cement that are coming out. Alternative binding materials are being considered. Low carbon clinker production, is being looked at, and then one of the things too they're trying to use as fuel sources is industrial byproducts, things like slag that already, aren't going to mean that the carbon footprint is going to keep being any bigger. So we are seeing effort being made, but right now, I think more than anything else, it is looking at how to balance out the reality of where it is, where it sits in line with maybe like the jobs that immediately affected, a lot of the financial implications of completely overhauling the technologies that are already on ground. So I think we are going to see a very interesting, landscape unfold in the coming years, especially around these so-called hard to abate industries like steel and cement. So yeah.
Yeah, and cement is a particularly difficult nut to crack, honestly, because the chemical process of creating cement, heating up limestone does release CO2. So that's kind of a fundamental step of generating cement. So Edikan was talking about trying to come up with different, pathways to that. But then there's just the high heat that is required to heat up the limestone in the first place, and that's very energy intensive. And so a lot of the challenges that we see, even with some of our carbon management processes like direct air capture, is just the energy demand that comes along, not with just with these industrial processes that we're trying to address, but even with the solutions that we're trying to address them with. The energy demand is always a critical problem, even when it's an industrial process like this. And so even if we can come up with, different mechanisms for, this chemical reaction of limestone that generates CO2 or capture that CO2, there's still the issue of how much energy we need to do these things. And that is kind of a central problem that you'll continue to come back to in the energy transition. So much as, even with these carbon capture facilities that is, more in my wheelhouse of study, is there's always this, what we call a parasitic load. There's always so much energy that you have to take off of that power generation plant just to operate your capture equipment. So it always comes back to energy for me, and why I think this, topic that you guys are interviewing people about and studying energy transitions in general is just really important to talk about.
Yeah,
And if I may just add one last thing to that. Um, so another thing that is also critical is to consider what is typically called a technological lifeline. What does that mean? Where you need to have seen something through a certain time period, see its impact, and to see the kind of sustainability angle to it. How has this actually, has this, could you necessarily call this a success? The kind of matrices that have to be looked at. And that now is also one of the things that we are beginning to see form because in as much as a lot of these technologies are revolutionary, we've not necessarily seen the effects. How does it cascade in terms of effects to every other component and every other aspect of society in that sense that is tied to it directly? So that is also something that I guess as we go into, this discussion of energy transition and looking at it from a holistic angle, that is an index that needs to be discussed more and more or less like be developed more into like something that can serve as a proper guideline because we need to see it through certain cycles. We need to see through, the realities of how the world economies look. Then we need to see it through the effect of that, on some sort of long lasting um, consequence as it pertains to life as we know it, in whatever form it is that these technologies are being implemented. So this is also a conversation that I know it's slowly forming, but it's something that is absolutely critical to this whole energy transition conversation.
Yeah, and Anna, as you mentioned before in your background being a program manager for carbon capture utilization and sequestration, um, could you tell us a little bit more about your research focusing on the geochemical impacts of injecting CO2 and also the geotechnical considerations when with policymaking?
Absolutely. That is my favorite thing to talk about. So there's really a couple different ways that geochemistry comes into play. And well, in the full value chain of carbon capture, utilization, and storage, there geochemistry touches all of those. But really what I focus on is the storage aspect and in the subsurface storage of CO2. And for that, there's again two ways that we use geochemistry. It's to model the deep subsurface intervals to see what happens when we inject CO2 into that specific lithology, so that particular mineralogic makeup that rock has, and the particular chemistry of the brine, the water that is in that reservoir. Also, we model the cap rock or the sealing interval and what its particular mineralogy is to make sure that no precipitation or dissolution reactions are going to occur that would negatively impact your ability to inject into the reservoir or your cap rock's ability to keep that CO2 in the subsurface. So essentially, we don't want to plug up our reservoir. We don't want to dissolve away our cap rock. So we build models that are based on data collected from the subsurface. So we take core samples down there. We run XRD, X-ray diffraction on those and get a very detailed mineralogic composition. We take water samples. We have a full suite of geochemical analytes to run, and we make a model that predicts how much precipitation dissolution reactions we have and make sure that that is not going to be a problem when we start injecting. And, the fascinating thing to me about injecting CO2 into the subsurface versus, extracting oil and gas, which has been there for millions of years, is really you are all of the sudden with CO2 injection taking everything out of equilibrium. You're taking pressure, temperature, chemistry, all out of equilibrium. So you have to be ready for what could happen because of that. So that's what we're trying to do when we build geocellular models of the subsurface. And that involves not just geochemistry, that involves geomechanics to make sure that we're not going to generate too much pressure, create faults or fractures, or reactivate faults or fractures that are already there. And we want to make sure that we are predicting the plume behavior, the CO2 plume in the subsurface and where it could go, and make sure that we can track it. So that's kind of one way that we use geochemistry. The other way is by ensuring that no environmental degradation has happened as a result of CO2 injection. So for the shallow subsurface environment, so these are your drinking water aquifers, soil, atmosphere, we take baseline measurements to make sure that we have a good handle on what this environment looked like before injection started. I shy away from the term natural baseline because often these environments really aren't at their necessarily natural state anyway, because human activities have already influenced them. But we take baseline measurements to make sure that we have a handle on those geochemical analytes in the aquifer specifically, sometimes soil, sometimes atmosphere as well, depending on the project, such that if there is ever a suspicion of a leak or there's an issue, we can test that water again and we can continue to monitor it throughout the injection process and after injection to make sure that there has been no effect due to CO2. And CO2 doesn't affect all the geochemistry in the aquifer, but it can acidify water, and that can have some cascading effects if it is intense enough. My research opinion or my findings through my PhD is that it would really take a catastrophic leak of CO2 into the aquifer to generate measurable changes that we would actually pick up in our drinking water. So that's very good news because it would be very difficult to cause negative environmental, effects. But it does make shallow environmental monitoring a challenge. Just those environments are dynamic. CO2 is naturally increasing in the atmosphere already. And so we have to kind of keep in mind that not all of the fluctuations that we see are going to be because of anthropogenic CO2. CO2 fluxes naturally in the environment, and it's kind of a fun problem, but it's definitely a challenge that it's a dynamic environment in the shallow subsurface.
And how does how does all that play into the policymaking decisions made?
Well, I think on the whole, there needs to be more conversation between the technical world and the policymakers. I think a lot of times there is a disconnect there. I saw this specifically in geochemistry. Some of the requirements right now to obtain a Class 6 permit. And I should take a step back, and say that the Class 6 permit is an extremely rigorous geotechnical characterization and full project characterization. Really, it's not just geotechnical that you must obtain to be able to inject CO2 into the subsurface. So and I think that's great. I think there has been a big pendulum shift or pendulum swing from what oil and gas regulations look like that kind of developed alongside the industry, because when oil was discovered, we didn't necessarily have regulations ready to go, compared to what's happening with CO2, where for better or worse, it's harder to inject CO2 than a lot of toxic waste products because the permitting process is a lot more strict. And so I think there are some I won't get into too much of the details, but I have seen in the geochemistry specifically some components that are required per EPA guidelines that I think could be updated to reflect some of the new science and some things that could be streamlined. But I will say it is so hard to regulate geologic projects because every single geologic system is unique. So I do not envy the job of the EPA to regulate and to permit these projects, because they give you this laundry list of things you must do to for your site characterization. But at the end of every kind of guidance section, there's this little addendum that says, but it's always project specific or location specific. So there's that little, I don't want to call it a loophole, but it is something that they need because every system is completely unique and must be treated thus. So it's tough. It's like, I think in my research, I came in initially kind of guns a-blazing, like, oh, they need to update this. Why doesn't this reflect the latest science? Obviously, there's a much easier way to detect whether it's anthropogenic CO2 in the subsurface. But every single project is so different. And there's challenges with every type of monitoring technique. And I think honestly, kind of throwing the book at these projects from a monitoring standpoint is more the way to go. Like, the Swiss cheese method, like, nothing's perfect, but if we add enough layers of protection, ideally we would prevent or mitigate any kind of risk that we have with CO2 leakage. So does that kind of answer your question?
Yeah. No, you bring up a lot of great points on both sides, on the industry research and also the policymaking side, just reaching not compromise, but some sort of middle ground, since it is so case by case. I
Yeah,
think it
and
brings a
I
lot
will
of
say
benefit.
some, jurisdictions are really good at listening to technical guidance. Colorado, as a state, has done an excellent job of listening to and collaborating with. Sorry, my dogs are barking. Sorry, listening to and collaborating with, technical research institutions, but and then incorporating that guidance into their rulemaking. So Colorado right now is going for Class 6 primacy, which is exciting. So that means that the state will be able to issue permits for CO2 injection rather than having to go through the EPA. But that's a it's difficult. I working closely with the policymakers in Colorado has shown me how difficult it is to take such such different guidance into their sorry. Sorry, hopefully you can edit that out. The dogs were just going crazy. So working with the Colorado policymakers has really been eye-opening. It's difficult for them to balance all of the competing interests and to come up with something that protects the public, serves the public, and kind of pushes these energy transition goals forward, and also listens to all of the researchers who are so head down in their own space and think that their issue is the most important thing to get into those policy guidelines. Again, I don't envy their job. I think they do in Colorado. I think they do an excellent job of it. But it's difficult, and I think the more dialogue we have between the technical community and the policymaking community, the better. Because right now we just kind of speak different languages, and we need to work on a more common vocabulary so that we can communicate better.
Yeah, I think you bring up so many great points. Thank you.
Well, do you think that Colorado being able to issue the Class 6 permits, is that a good thing? Because if that's like, I'm assuming that would be out of line with the EPA regular. They would have different sort of set of standards. Do you think that's a good or bad thing? And could you elaborate a little bit on the benefits and drawbacks of that?
Absolutely. Absolutely. Yeah, I feel pretty strongly that it's a good thing. So the way that primacy works, and right now the states that have primacy are North Dakota, Wyoming, and Louisiana. And it is the burden of the state to prove that their rules are just as, if not more strict than the EPA's. So establishing primacy does not mean that states get to say, okay, well, the EPA made you do this, but we're going to let you, get away with XYZ. It doesn't work like that. You have to meet all the hurdles that the EPA had required. I think that the power of primacy truly is that you are in the state of Colorado, we are giving it to the ECMC, the Energy and Carbon Management Commission, formerly called the Colorado Oil and Gas Commission. They have a familiarity with the state, with the land in the state, with the subsurface formations in the state that the EPA just does not have. The EPA is broken up into regions, and Region 8 encompasses a huge area outside Colorado. And to expect them to be experts on all of the subsurface formations that might be prospective for CO2 injection is just not realistic. They also just don't have the manpower. And I'm not saying the state is, overly, staffed up or anything like that. But if you just look at the numbers right now, the EPA has issued, I believe, as of last week when I looked, a total of 6 permits total nationwide from the EPA. North Dakota has issued 6 itself. Wyoming, after having primacy for only a few years, Wyoming has issued 2, and I think Louisiana is reviewing several, but they just recently got primacy. So, I mean, the numbers would suggest that primacy streamlines the permitting process for projects, and honestly, with the numbers that the gigatons of CO2 that we are being told we need to address from the IEA and IPCC via carbon storage in the subsurface, getting these projects online quickly is critical. So yes, I think primacy is a great thing. I did get to work with the state of Colorado on some of their plastics rulemaking a bit and went on a public kind of road show around the state of Colorado and visited a bunch of different communities to talk to them about the plastics rules. And one of the great things about states being able to do this is they can include provisions about community benefits and how communities can vocalize their either support or opposition to the projects. And Colorado gives a lot of control to local municipalities to push back on industrial development that they don't want. They are, Colorado has outlined these goals so that we don't kind of further environmental injustices that have already happened. And the challenge with, carbon storage and carbon capture is that you're usually putting these in industrialized areas already. So you don't want to just double down on these areas that have already been adversely impacted. So, giving some power, the Class 6 being put under the state of Colorado provides even more power to those local communities to have a voice in the process.
And so you're basically saying like it's basically the benefit of time, I guess. That's the most important thing for primacy. Because I think so the EPA is lagging behind, and Colorado's also with the states' rights. I think it would be better to engage the communities within. And so it's easier to customize it basically for each case.
Absolutely. Much easier to customize it, much easier to hear and incorporate community feedback. Often the companies that are going to be operating Colorado are companies that already have been operating in Colorado in a oil and gas capacity or other ways. So the ECMC is familiar with them. It's not starting from scratch with reviewing a permit like with the EPA. And I'm not trying to negatively paint the EPA at all. They have been inundated with permits, and they have a laundry list of things to review. And these permits are dense, and they are often 700 to over 1,000 pages long. And that's geologic characterization, that's financial assurance, that is your pipeline plans, your everything. I mean, it's a lot of information. It's a lot to review. It's a lot more to review if you don't have familiarity with the area. So I think that's one of the big powers of primacy for the state.
Mm-hmm. Well, I don't want to interrupt this amazing conversation about primacy, but just circling back to green steel, one example that I've seen is the Evraz Rocky Mountain Steel Mill, which is closer to you guys than over here at USC. But they've recently been moving towards solar. So can you tell us a little bit more about that and green steel in the context of that mill?
Great. I think I'll jump in here. So one of the things that makes the Everest Rocky Mountain Steel project interesting is it sort of brings in every component of what we're talking about in a way. So Everest by itself has been in operation for over 100 years. So you're looking at something that has, obviously lived through different technological, life cycles in some sense. And now it is the first of its kind, like to be the first North American steel mill factory that is completely 100% powered by solar, right? So they have these collaboration with a company called Lightsource BP. Lightsource BP in itself is also an interesting component because Lightsource BP is there is a company that was started in 2010 called Lightsource Renewable Energy in the UK. And BP, British Petroleum, one of the biggest oil and gas, known for oil and gas, bought at the time, it started off with 43% and eventually increased its stake to 50%. And it is like a company that is now 100% like solar energy provider. And so Lightsource supplies 300 megawatts of power that is completely solar generated to Everest, right? So the sheer scale of this in itself means that you're looking at about 500,000 tons of greenhouse gases that are just being reduced by that operation going completely solar. But to tie everything that like we said here and what makes this Everest project so interesting is that you're looking at a steel mill that is a whole century, like a century old, has been in production, and yet is able to make this transition without necessarily paying a halt to its operation. And this now sets some sort of precedent in a way to show practically like that it is doable, it is attainable, where um, you don't necessarily have to completely like do the grounds that you already have as far as like your production. Nobody really needed to lose their job in some sense, and their customers are still being serviced. And so right now we're looking at this as a success story that is setting the precedent for traditional steel mills who want to slowly make the transition. Because I mean, there are instances where there are companies that there's a company called Boston Metal, right? That is like completely 100% green steel, but it just started like in recent times. So they're able to like incubate this technology from the get-go. But Everest is so interesting because Everest has been in operation for 100 years, and now we are seeing this transition to being completely solar powered. So it's interesting, and I mean this also speaks like Anna mentioned to maybe like how the state of Colorado is beginning to provide like a very conducive environment that takes all these components into consideration and not necessarily just coming with, because there are places that could possibly have been a lot more draconian, this or you shut down completely. So uh, the enabling environment that this has created set the precedence for the fact that it can be done. This is a success story that one can replicate, in other places. So yeah, Everest is an interesting case study for us, and I think we spoke briefly about it in the paper, I believe, because it really sets the tone and the precedence for what is attainable in practical terms. Yeah.
I think changing existing infrastructure is really important because that kind of pushes that idea of upgrading rather than building anew, right?
Yeah,
And this whole
that's
idea
correct.
of
Yeah, yeah,
important, right? Hmm.
that's absolutely correct.
Yeah, and with all these efforts and research and funding that goes into these decarbonization efforts in the industrial processes, what is it going to take for these innovations to reach a scale that makes a difference in these efforts, while also meeting the global demand for these critical processes?
God, that's like the $1 million question, I would say, how to scale.
Yeah, scale.
It always comes back to that question. I mean, there are uh, thousands of just like incredible innovative concepts and innovative techniques that work. They work at the laboratory scale, they work at the demonstration scale. Scaling them up is difficult because industrial
Mm,
scale is just enormous, and
mm,
and the challenges are different for every industry. So I'm heartened by the fact that we have a lot of incredible research going on just at Colorado School of Mines. I'm sure the same at USC.
mm,
Um, that that shows me, even just here we have such a broad range of research digging into those really technical questions about, how do we generate bricks that capture CO2? That's happening in our
mm,
school. How do we use steel slag to capture CO2 that would just,
mm,
normally be a waste product? Um, how do we use these things that are being generated already, and how do we enhance natural processes that occur innately? How do we encourage those to capture CO2 faster? Um, but scaling up is always the big challenge. And again, it's an energy demand question. Some of these processes work, but they are just so energy or water hungry that they're not practical for a lot of areas. And it's not a an easy answer to this question, but what it's going to take, I think, is every community looking at what solutions work for them, and what's practical for them, because what works for a community, proximal to a bunch of refineries on the Gulf Coast of Louisiana is not going to work for Boulder, Colorado,
for
is not
sure.
going to work for some, New York City is not going to work for,
Mm,
anywhere on the East Coast. So I've just a quick story. We in one of those visits to Durango, Colorado, we had a citizen get up and say she was really upset that they wanted to put a solar farm in. And I was a bit surprised because I'm there ready to take pushback on all the carbon, sequestration questions. And but their biggest concern is fire risk, and the lithium batteries that accompany the solar farms was really unnerving to that population because they are so at risk for fire. So I think having those conversations and just understanding that no technology, no industrial process, no technology, no green energy tech is without challenges and without a downside. So kind of trying to figure out how to do the least harm, and Edikan touched on kind of life cycle analysis a little bit earlier without necessarily calling it that, which is probably good because that opens up a huge can of worms for some people. It's a whole field of study, and won't get into that. But we have to make sure that we aren't trying to do something for the greater good that is going to forget about the communities in which we're putting these technologies. And so, sorry, I've deviated from your scale question a little bit, but that's all to say that, it's going to look different in every community. It's going to look different for steel than it does for cement. It's going to look really different for direct air capture out in, rural Nevada, Colorado, Wyoming than it does in, retrofitting an existing power plant to capture the CO2. All of those solutions are going to look really different. A little more directly answering your question, I think there are some really exciting technologies coming out in modular capture. So, right now, most of the CO2 capture that's being put on emitters, so your point source emissions, so not direct air or anything, or not carbon dioxide removal, but emissions mitigation, they are built on site. They are bespoke, and fit for purpose for that one plant. And it's essentially like building a whole nother power plant adjacent to it. It's complex, it's expensive, it's time consuming. But a lot of innovation is happening in this modular capture space where these units are built offsite. They are built in this other location factory, and they can be scaled up or scaled down depending on the size of your project. You can put 20 units on site. You can put 1 unit on site depending on what you need. It makes the construction and the timeline to get up and running much shorter. It also opens up a whole new world of addressing the mid-size emitters. Like right now, people are really only talking to the massive emitters because that's where there's the economies of scale. Like if we're going to build this, we want to get the bang for our buck. You're not going to build it on like the local incinerator at the garbage dump in some small town. You're not going to do that because it's not worth the investment for the amount of CO2 you're going to capture, and thereby the amount of 45Q tax credits that you're going to have access to. So it opens up, I think the modular capture space is exciting because it opens up a broader scale of emitters. And depending on the tech, there's cryogenic capture, there's amine capture, there's all these different types of capture. It can address different types of emissions. Some are better at different things than others. Again, it has to be fit for purpose. But yeah, there's even Mitsubishi's come out with something, and there's a paper that called it bite-size capture because it's like these really small units that can be put on, like an apartment building or some moderate size emitter. There's a whole nother conversation to be had about transport of that CO2 once it's captured and the challenges with that. But yeah, I think the modular space is a really exciting kind of space for innovation as far as scaling up goes.
Yeah, and you commented how these decarbonization efforts are very location-based. As a whole, with Chinese and Indian companies being key producers in steel and cement, do we see these decarbonization efforts being pushed mostly on the West? And do you know can you give insight into what's happening with these large producers?
The world is becoming a lot more globalized in some sense. I mean, we've seen the likes of the Paris Accord, and efforts of that nature to bring a global level of attention to, greenhouse gases and its effects and all, like generally just leaving this world better than we met it in some sense. One of the things, though, that I mean, like I'm speaking first of all, before even going maybe to speak about India and China, speaking first to my experience as an African, because all of my working career like has been a lot around the African mineral space. Um, the economics of these things are things that have taken precedence and to an extent continue to take precedence over maybe the sustainability angle to it. Um, Now, one of the things that like we, and I know we are looking at the West. So here we are talking about 100-year-old steel mill in Colorado, which isn't even the oldest steel mill in America. So you're talking about like 100-year head start that there has been generally to industrialization. And what we are beginning to see, China, for example, I guess this big boom isn't even quite 30 years old. If it's at most, it's not even quite 35 years old. And then so we things taking some sort of natural cause in that the components of industrialization that first have to take preeminence in that in the way like the being able to create all these viable jobs, the economics of it, catering to the built environment on your end. Those things are what we've seen go ahead of it. But right now, I can say that China is aggressively also investing in steel decarbonization. There are some efforts that they're seeing. The West is the champion of it, but we are seeing a case where the rest of the world is now taking like full cognizance of it and coming into a place where it's a conversation that is being had. So even here, if we take North America as an example, um, we have not even achieved scale, right? Of the efforts haven't necessarily been able to like we've not been able to replicate it all across, like industry wide, efforts. So I would like to say like if we look at it from where we stand right now, one of the things too that is happening is that the big demand that the rest of the world is beginning to place. Like you're seeing, for example, in Europe, Volvo is saying, look, we want purely green steel. Like if you're going to supply us steel, they've given a certain benchmark by which time you say all the steel that you're going to supply us has to be green. But this is because, I mean, there are already infrastructure in place that can cater to that. So the conversation around getting China and India to come into the place where we see in the West is one where um, um, we have to be able to typically, right? So in my world of data analysis and operations research, there are things we call penalty variables, right? There are certain things generally when you're putting together an objective function, when you're looking at something, you need to be able to put in certain variables that scale your problem in a way that is realistic in some sense. And this is now where I guess that conversation is being had. Whether or not um, adherence to it is going to be 100% remains to be seen, right? We are just coming into the place where, first of all, they need to be able to cater to their industrial needs. And then at that point is when this conversation will now, be able to take on the form where scale is now, of consideration. So we will see the world as it is. One of the things I'm happy to see generally when it comes to things like the Paris Accord is that you are being held liable. Like like there's a level of for you to gain certain access, they expect you to play by certain rules. And I see us eventually getting to a place where as the West also scales, the rest of the world will scale. So this conversation is one that I believe we are seeing unfold. I wouldn't necessarily say that we should count them out, but it's just we should be a lot more mindful of the realities that surround, how exactly they are coming to play in the market. But I do see, I think I'm highly optimistic that we would soon see a scenario where, all across board, everybody, adheres to these rules. And I believe in our lifetime, we'll see green steel just be mainstream, just the way traditional steel is. So yeah.
That would be awesome. I'll also add to that, there's some practical components to this that make it so much harder for different nations to decarbonize steel specifically. And I mean, that's from the iron ore that they have available to them, like the quality of the iron ore, to what their, main energy sources. Like if that's coal, they build coal, blast furnaces.
Yeah.
Most of our steel production, and correct me if I'm wrong, Edikan, but is electric
Yeah.
arc electric furnaces. So it's a lot easier to decarbonize that process than to decarbonize a blast furnace that's based on coal, burning coal. So there's that. And then also just, and Edikan touched on this already, but the exponential growth in population and just industrialization that's expected and has already been seen in India, that will be hard to meet that demand. Like they have a lot higher demand coming than the US does necessarily. So it's a bigger ask for them to kind of revolutionize that whole industry. Is it possible? Absolutely. And I think Edikan's right that global demand and requirements for green steel will drive that. But I think it's harder for different. I mean, there are practical reasons why it's more difficult for some areas of the world to decarbonize steel in particular. And that just adds a whole nother layer of complication to it. That adds a whole nother layer of economic challenges. And then how do you bring that to market? How is that reflected in the price of this green steel that you are bringing to market? So I think it's complicated. It's an big picture global economics question and challenge.
Yeah. What Anna just said, it's actually, thank you. You just reminded me of something. Cost-wise, right now, the cost of green steel to traditional steel is almost a 10 to 1 cost as it is right now. So, technologically speaking, it's much more expensive to produce green steel. And for like as she has rightly put it, like when you're still trying to get everything up and running, cost is such a big component. And and I know that we've seen it in every other industry where technology has just grown to the scale where cost has been something that we've seen being driven down, a lot. Agriculture, for example, I mean, I'm sure that when we started seeing industrial scale agriculture, it was a lot more expensive than what we see today. So I think this thing is just taking the course that it will take in that regard. But we are beginning to see a lot more consciousness from the end users of steel who are beginning to say, look, we're giving you the next maybe 15 years or whatever. At that point, we want all green steel. And technology is evolving. Anna touched on the fact that there's a lot of research that is going on in Colorado mines already. And that's just one of many. And this is even just in the academic environment, in the industrial environment as well. There's a lot of research going on. So I am really optimistic, but then we just have to, look at this with, like real matrices of the true impact of going green just all at once to come to countries and industries in countries where some of them haven't even recouped the capital cost of setting up, the facilities that they have. Some of them, still have not even achieved the full scale to be able to meet the sort of demands that they want. So these things will obviously be the things that will be the precedents, the constraints that need to be met prior to us being able to fully engage that conversation. But I know we will see adherence to this in our lifetime, like on a global scale. So, yeah.
Yeah, you guys bring up again such great points on the feasibility of everything, especially being location based and demand wise as well. I think it really demonstrates, the reality of what can be done. So thank you.
Thank you.
And Edikan and Anna, thank you so much for being here today. And if there's anything else you would like to leave our viewers with, please let us know or just tell us right now. And thank you.
Yeah, thank you so much.
Yeah, thank you for having us.
We want traditional industries to stay relevant during sustainability efforts. We can use skill sets from oil and gas and other industries, industrial industries that will apply to decarbonization solutions to do so.
What is green steel? Traditional steel uses carbon as fuel and well as a reducing agent. Green steel uses hydrogen as a reducing agent instead of the carbon, also known as metallurgical coke, and uses electrical arc furnaces for heating, and carbon capture integration included.
We need to be working on solutions in the energy transition that do not leave whole communities behind. Steel and cement are fundamental to economic society, and the energy transition will mean an industrial transition as well.
And what about green cement? Researchers are trying to find alternate reducing agents as well as alternate fuel sources.
The impact of geochemistry is critical on analysis of subsurface storage and groundwater through carbon or carbon dioxide sequestration.
And there's a need for more conversation between policymakers and geotechnical experts. There can be a disconnect. And one example is the permitting process for carbon injection wells with state primacy. It's very difficult to regulate geological processes as almost every system is unique depending on the location. And another example is for monitoring and measuring these technologies.
It's been an eye-opening experience working with the state of Colorado regulators to trying to balance all the factors and all the priorities of all the stakeholders.
And as we heard, we got to give more power to the local communities to say if they want industrial activities and if they don't want to double down on communities where past injustices have been committed.
One example of this is when the Evraz Rocky Mountain Steel with Light Source BP in Pueblo, Colorado, they'll be the first steel mill in the US to be totally solar. Their steel mill is over 100 years old and still making this major shift.
The million-dollar question is, how do any of these new ideas get to scale? Scaling up is always the difficult question. There's no one-size-fits-all problem, and it will take each community finding what works for them. There's no green technology that comes without its downsides. So a solution that is for the greater good may cause harm for local communities.
The potential for the bite-sized capture and modular scale approach was also explored in this podcast.
And today, the cost of green steel is 10 times that of traditional steel. So economics are a key issue.
Well, our two guests closed on an optimistic note. They said in a few years' time, we'll be saying, can you believe we used to do it this way? The future holds promise. Be optimistic. We are on the cusp of developments that will change the world.
There is a lot of news about nuclear energy these days, but a lot of it is confusing. One article talks about closing down nuclear reactors before their permit dates, and other articles talk about renewed interest in new versions of nuclear power plants. Luckily, in this episode, we have Dr. Naj Miskati, Professor of Civil and Environmental Engineering, Industrial Systems Engineering, and International Relations at the Viterbi School of Engineering to help us figure this all out.
I read that Microsoft is in negotiation with a power utility company to restart one of the units at 3 Mile Island, a facility in Pennsylvania where a big safety accident happened in the 1970s. That's a huge U-turn in our demand for power. The energy transition is not a one-way street, as we've seen before.
There are still challenges in nuclear power, such as capital cost in building the plants in the first place, and getting rid of the radioactive waste as the plants operate. But there are new ideas and solutions as well, including a new design called a small modular reactor, also known as SMR.
Well, as usual with these new forms of energy, China is in the lead of building new nuclear plants. Even a fourth generation plant at Shidawan is being created right now. The Barakan nuclear power plant in the UAE is the first nuclear reactor in the Middle East. We don't want to close the chapter on nuclear energy just yet.
There is an article that was written about me in Viterbi School of Engineering magazine, I think in 2021 or 2022. During the COVID, it was in Viterbi magazine. The title of the article is Accidental Professor. That's the title I suggested to the author. I'm an accidental professor because I studied engineering back in Iran, industrial engineering at Sharif University of Technology, which we like to think of it as MIT of Iran almost 40 plus years ago, before the revolution. And then because of my interest in international relations, political science, I double majored in another university in the evening in political science and international relations. And I used to carry between 40 to 45 units per semester for 4 years. But when my students, they ask me, they tell me that they have 2 exams in one day. I say, you are talking to the wrong person. My record was 5 exams in 2 days.
Wow.
And human factors issues and that basically put me on this path of looking at human systems integration and interaction, human technology interaction and integration, because many people attributed that accident, 3 Mile Island nuclear plant, to operator error. And then a few years later, on December 3rd, 1984, Bhopal chemical plant accident happened. That was a release of methyl isocyanate, toxic gas from the Bhopal chemical plant of Union Carbide in city of Bhopal in Uttar Pradesh in India, that killed overnight 2,000 people and injured 200,000. And out of that 200,000, unfortunately, on the average, 2 are dying per day. And when we commemorated its 30th anniversary in 2014, pretty much we are commemorating its 40th anniversary on December 3rd, 2024. The number of deaths reached to almost 30,000. And then 2 years later, Chernobyl accident happened. Chernobyl nuclear plants in now Ukraine, at that time Soviet Union, on April 26, 1986. That's considered to be the world's most important technological system failure and accident because of the radiation release and all the mass evacuation that it caused. And that was attributed also to the issue related to my area of interest, which is called safety culture. These events, 3 Mile Island 79, Bhopal 84, and then Chernobyl 86, that was the first 3 things that happened, one after each other, that put me on this path.
Thank you so much for joining us for the Future of Energy. Special thanks to each of our guests today and to our technical wizard, Abhi, for his important contributions to this episode. Don't forget to subscribe to our podcast so you can automatically get access to all our new episodes. You can find us on Apple, Spotify, YouTube, or wherever you get your podcasts.